Hello everyone, this is Abhishek Mohanty and you are watching Padarth Vigyan. So students, in this video we are going to do a derivation from the chapter Electrostatics. The question is on the screen. So in the video we are going to derive an expression for the electric field at the axial position of a short electric dipole. In your exam you may get this type of derivation. So let's do it. We know that an electric dipole consists of two equal and opposite charges separated by a small distance. Now I have to draw an electric dipole. So this is the electric dipole where I have taken two equal and opposite charges, minus q and plus q. At the point A, charge plus q is present. At the point B, charge minus q is present. Suppose O is the center of the dipole. Means O is the midpoint of the line joining the two charges plus q and minus q. Now assume that the dipole length means the distance between the two charges is 2a. 2a is the distance between the two charges. Since O is the center of the dipole, it means the distance from B to O is A. Similarly, the distance from O to A is also A because O is the midpoint of the dipole. Now we are going to find the expression for the electric field at the axial position of this dipole. So what is the meaning of axial position? Axial position means any point lying on the axis of the dipole. So what is the axis? Axis means I have to extend the line joining the two charges. So now I will extend the line like this, and on this axis I can take any point. Suppose I'll take a point M here. So M is called the axial point. Now my task is to find the electric field strength at that point M. And assume that the distance of the point M from the center O is R. Okay. Now look at the question. The question is saying that we have to find the electric field strength at this point M due to is short electric dipole. So what is the meaning of short electric dipole? Short electric dipole means the dipole length, which is 2a, it should be much smaller than the distance of the axial point, which is r. So 2a should be very small than r. Or I can say that a is much smaller than r. So this is the condition for the short electric dipole. So to do the derivation, we should have a knowledge about the formula to calculate electric field due to a point charge. Electric field due to a point charge. So all of you know that if we have a point charge q here and we have to find the electric field at a distance r, then the formula is E equal to kq divided by r square. This is the magnitude of the electric field. K means the Coulomb's constant, which is 1 by 4 pi epsilon naught. Q is the magnitude of the charge and R is the distance of the point from the charge. So K, Q by distance square is the formula for electric field. But we know that electric field is a vector quantity. It has magnitude as well as direction. So this is the magnitude of electric field. But what about direction? Remember that if we have a positive point charge, then the electric field is directed away from it, directed away from the positive charge. And if we have a negative point charge, then the electric field is directed towards the negative charge. So this is about the direction. Now look at the dipole. In the dipole, we have two charges. We have a positive charge, we have a negative charge. And both the charges will produce electric field at the point A. So now we have to write the expression for electric field due to both the charges, due to the positive charge as well as due to negative charge at the point A. So first I write the expression for electric field at the point A due to the positive charge, E plus Q vector. So to find the value of electric field at the point A due to the charge plus Q, first we have to find what is the distance of the point A from the charge plus Q. What is this distance? Means the distance from A to M. So from the diagram you can see that the distance from A to M will be R minus A, because O to M is R, O to A is A, so A to N will be R minus A. So what is the formula? The formula is K into magnitude of charge, which is Q, divided by distance square. The distance is R minus A, so I'll write R minus A whole square. Okay, so this is the magnitude part. But as you know that electric field is a vector quantity, so I must write the direction. I had told you that if you have a positive charge, then the electric field is directed away from the charge. So at the point M, the electric field due to the plus Q charge will be directed away from it, means towards right. This is the direction of E plus Q vector. Okay, so the question is how to write the direction part. We know that in vector form, when we want to write direction, we have to use the unit vector. And we know that the dipole moment is directed from negative to positive charge. The dipole moment is directed from negative to positive charge. So in the diagram, at the point B, we have negative charge. At the point A, we have positive charge. So for this diagram, the dipole moment is directed from left to right. Okay. So if I write P cap means a unit vector along the dipole moment. P cap means the unit vector along the dipole moment. So P cap is directed from left to right. Okay. Since E plus Q, the electric field due to positive charge is directed towards right, I can write P cap. So P cap is a unit vector which is directed from left to right in this diagram. That's why this P cap will denote the direction of E plus Q vector. Okay. Now, what is E minus Q vector? Electric field due to the negative charge. Again, the formula is K Q. Q is the magnitude of charge. Don't write minus sign here, because when you're finding the value of electric field, only write the magnitude of charge. Don't write the sign. So it is KQ divided by. Now tell me what is the distance of the point M from the negative charge minus Q? Means the distance from B to M. So again, from the diagram, you can see that the distance of M from the point B will be R plus A, because M to O is R, then O to B is A, so it will be R plus A. So I'll write R plus A square, and the direction will be towards the negative charge. For a negative charge, the electric field is directed towards the negative charge. So this is the direction of E minus Q vector. And it is opposite to P cap, because P cap is towards right, but E minus Q is towards left. So I'll write minus P cap vector here. Okay. So in this way, you can write the magnitude and the direction of electric field. So now we have two charges, we have two electric fields. So we have to find the net electric field. It means the total electric field at the point M. Since M is the axial point, we call it axial electric field. E axial vector is equal to the vector sum of the two electric fields E plus Q and E minus Q. So E plus Q is KQ divided by R minus A whole square P cap, plus E minus Q is KQ divided by R plus A whole square minus P cap. Okay. So in the next step, what you have to do? You can take KQ common. In the bracket, you'll have 1 by R minus A whole square. Then this plus and minus becomes minus. So it will be minus 1 by R plus A whole square. And outside the bracket, write P cap. That implies it will be KQ. If you take LCM, it will be R minus A whole square into R plus A whole square. In the numerator, you will get R plus A whole square minus R minus A whole square whole into P cap. That equal to KQ R plus A whole square minus R minus A whole square will be 4RA divided by, in the denominator, you have R minus A whole square into R plus A whole square. It will be R square minus A square whole square. Then write P cap. So the next step, KQ, this 4RA can be written as 2A into 2R divided by R square minus A square whole square P cap. So Q into 2A. Q into 2A means the dipole moment P. We know that the dipole moment is given by the magnitude of either charge into the separation between the two charges or the dipole length. So Q into 2A will become P. P means dipole moment into, we have 2R left here, divided by R square minus A square whole square, and P cap is the direction. Now let us go to the condition given here. It is given that the dipole is a short dipole. It means the dipole length is very small as compared to R. It means A is much smaller than R. So if A is much smaller than R, I can say that A square is very smaller than R square, or R square is much greater than A square. So in that case, R square minus A square is approximately equal to R square, because R square is very large, A square is very small. So if you subtract a very small quantity from a very large quantity, then the value remains almost the same. So R square minus A square is almost equal to R square. So in this expression, I can make some changes. In the denominator, I have R square minus A square. So this value is almost equal to R square. So R square, and I have another square here. So it becomes KP into 2R divided by R to the power 4. So R will cancel, you'll get K into 2P divided by R cube. And here, don't forget to mention direction, this is P cap. So K into 2P by R cube into P cap. So finally, we got the expression E axial equal to K into 2P divided by R cube into P cap. So this is the final expression for the electric field due to a dipole at its axial point. So students, I hope that you have understood the derivation. This question may come in your exam. So you have to do the derivation like this. First, write the expression for electric field due to both the charges, for positive charge, for negative charge, then add them pictorially, and finally take this approximation and you get the answer. The answer is E axial vector is equal to K into 2P by R cube into P cap. So that's all for this video. In the next video, we'll do another derivation. So till then, have a nice day and bye bye.